Okay, folks, welcome to our video on depth perception. You should have your notes out, and you should be able to pause and keep notes, keep track of notes for yourself so you can rewind and pause if you need to. What we're trying to identify here for objectives is the ability to describe and explain how depth perception occurs. We're going to be talking about the visual cliff. We're going to be talking about binocular cues and monocular cues and the ability to use these cues to explain how we perceive depth and distance visually. So we're going to start off with a question: is depth perception innate or learned? One of the more famous experiments in this realm of discussion, when we talk about depth perception, is the Gibson and Walk study of 1960. I believe it was at Cornell University. And Gibson and Walk, they wondered if babies would crawl over the edge of a cliff. Was depth perception innate, or was it learned through experience? And we know that infants, by the time they crawl, have a wealth of worldly experience, but they also used newborn animals in this experiment. So in their lab, they created an artificial cliff, something like this here, where we had a shallow end and a deep end, and we had some glass on the surface of both sides. So there was a piece of glass on a textured surface that was right in here where the baby is currently sitting. And the piece of glass extended all the way across the top. But to the baby, it looked like if they went beyond this edge here, that they would fall off and go down to the bottom. So it was a drop off. And mom was trying to coax that baby across that ledge, but when most of the infants got to that edge of that textured pattern, they stopped. They did not go over the edge, which showed Gibson and Walk that at least by the time they're mobile, they have this perception of depth. They also used day-old kittens and goats and newly hatched chicks, and they did not go over the edge either, which Gibson and Walk concluded then that at least by the time we're mobile, we have this built-in system to detect depth of the protection thing. So as we move on, how do we perceive depth and distance? There's really two visual ways that we determine depth and distance. One is called binocular cues, and then the other is called monocular cues. And you can probably guess that binocular cues actually require the sight from both eyes. This is an innate experience. We're born with this capability, and this helps us determine depth, especially of objects that are closer to us. Now, one of those binocular depth cues is called convergence. And what that refers to is the ability for our eyes, as an object moves closer to us, that our eyes kind of converge towards the center of our face. And as they do that, the ocular muscles that control the direction of our eyes are sending signals to our brain that our eyes are turning inward, and our brain then perceives objects as closer. So if you remember when we talked about kinesthetic senses, our muscles do send signals to our brain about their position. So as we look at this model down here, remember that as our eyes focus in the distance, so when we focus on something pretty far away from our eyes are fairly parallel. So when they're looking straight ahead, our brain tends to perceive those objects as in the distance. But as objects move closer to us, there's an inward turn of our eye, and you can kind of see, if we're looking at an object here, how our eyes have to converge in, and this angle in here is calculated by our brain to create this perception of an object moving closer to us. And as an object moves even closer, we have an even sharper inward turn. So this angle increases here, and that leads us to perceive depth. Okay, that's one of the binocular cues. Another binocular cue is called retinal disparity. So basically the disparity here means difference. And our two eyes do send separate views to our brain, which then combines the images and overlaps them in higher level processors. Remember feature detectors and parallel processing. We perceive depth. And I think we did this little activity in the classroom. Although we didn't have trees in the classroom, this is a good little diagram that if we're staring at our finger as it's held out about an arm's length away from our face, objects in the distance, we tend to see basically two images in the distance. So the trunk of that tree, if we're staring at our finger here at an arm's length away from our face, distant objects appear to have two images. And then if we refocus on a distant object out here, in our field of vision, it looks like we have two fingers. So that kind of shows us that we do have this disparity, that each eye sends a different message, and that through parallel processing and hyper-complex visual detectors or visual processors in our brain, we have to overlap these images in order to see one, which kind of creates this 3D image. And you can try that. You can try that at home if you'd like, but we'll try it in class as well. We already have. Now this brings us to monocular cues, and I'm going to stop there, and we will add a feature a little bit later when we talk about monocular cues. Heck, let's talk about them right now. I'll try and get this done in under 4 or 5 minutes. So monocular cues require the use of one eye, and this is based on experience. So these are learned visual cues. And if you remember the mnemonic device right here, that the first letter each means or represents one of the monocular cues. Some boys can have interesting lives tomorrow, maybe. So remember that monocular cue mnemonic device. So basically here are the monocular cues. Require only one eye to perceive depth. We have relative size, which means objects that cast a smaller retinal image are perceived to be farther away if we assume they're the same size. And I'll show you some examples of this in a moment. Relative brightness refers to the sensation, perception that closer objects tend to reflect more light to our retina. So as objects are brighter, they tend to be perceived as nearer than objects that are less bright. Relative clarity is kind of an atmospheric principle, so it doesn't work in a classroom maybe, but when you're looking out over a great distance, objects that appear less clear are perceived to be farther away from us than objects that are clear, which might cause driving in the fog a little bit more dangerous because we might think we're farther away from brake lights than we really are. Relative height suggests that for objects that are on the same plane, if they appear higher in our field of view, they are perceived to be farther away. So if we look down by our feet, those are very low in our field of vision. And as we look up, we might see the bottom of the table leg higher in our field of vision, and we perceive that to be farther away. Interposition refers to objects that block our view of another are perceived to be nearer. So anything that objects that are in front or perceived to be in front of another object, we think it's closer than the object that's being blocked. Linear perspective deals with assumed parallel lines like the edges of a road or railroad tracks or of a ceiling, for example. We assume that as the parallel edges appear to get closer together, that they're actually in the distance, more distant. Texture gradient which is the tomorrow, and some boys can have interesting life tomorrow maybe, suggests that the more clearer and distinct a texture is on an object, the closer we perceive it to be. And as objects lose that distinct texture, we perceive those objects to be getting farther away. And then there's another one here called relative motion. This basically means as we move forward, as we're actually moving, objects that move out of our field of vision more quickly are perceived to be nearer than objects that move more slowly out of our field of vision. So we have to be moving for that one. I'm going to take a look at some examples right now. We're going to switch screens here, if we can, for a second. We're going to go to this scene. And basically what we're trying to look at here in this visual scene is how do we know building B is farther away than building A? And if we look at our monocular cues, we can see relative size here, that if we assume two objects to start out as the same size, yet one casts a smaller retinal image, like this one, like this building casts a smaller retinal image, measure it with your fingers if you have to, then this one, we perceive it to be farther away. Relative brightness, objects that appear brighter in our field of view, this block appears brighter than this block, we perceive it to be nearer, and this building's casting more light to our retina than this building, so we perceive A to be nearer to us. Relative clarity is that distance, atmospheric position. Objects that are less clear, like objects out here, a little hazy, are perceived to be farther away than objects that are clearer to us. Again, an atmospheric monocular cue, if you will. Height, relative height, that objects, if we assume this is a flat surface here, as objects move up in our field of view, at least if they're below the horizon, they are perceived to be farther away. So if we look at these two objects here, we don't think they're different distances, but this object here that moves up, we perceive it to be farther away. Now the opposite would be true for objects that are above the horizon. Interposition or overlap, when one object partially blocks the view of another, we perceive that blocking object to be nearer. So if building A blocks another building, which blocks something else, which may block other buildings that we perceive in the distance, certainly those objects are perceived to be farther away. And linear perspective, assumed parallel lines, as they converge, are perceived to be more distant. So not as obvious in this picture, but we can certainly recreate it. Now the motion parallax one, remember you have to be moving, so you can't see this in a still photo, but if we look at this object right here, it seems to be moving faster out of our field of vision than this object, the slower moving object. So we perceive the faster moving objects to be nearer to us than the slow moving objects. That's relative, or motion parallax, okay? So distant objects appear to move more slowly than faster objects. So if we go back to our depth perception notes here, that's it for depth perception, monocular and binocular cues. Remember to be kind and rewind, and use your notes. And we hope this went well for you. So that's it. Good luck. And